Hello, my name is Wes Colangelo, and today I will be covering Tygacil, which is an antibiotic that was introduced to the market in 2005 by Waith Pharmaceuticals under the brand name Tygacil. I chose this because I am also currently involved in antimicrobial development, so I thought it might be interesting to cover this particular antibiotic. So, as most people are familiar with, antimicrobial antibiotic resistance is on the rise, and some of these statistics are a little dated, but they are referenced, as you can see, and the last slide of the presentation has these references. So in 2002, it's estimated 1.7 million hospital-acquired infections occurred, of which 99,000 were fatal. If we compare this to 2008 morbidity statistics, hospital-acquired infections would be the 6th leading cause of death in the United States. So a large medical need is there. 2006-2007, 50% of Staphylococcus aureus infections were methicillin resistant, and 56.5% of E. faecium infections were vancomycin resistance, also known as VRE, and the former is MRSA, or MRSA. And finally, we see that there is a increasing rate in the resistance levels observed, especially with MRSA. And here's a graph showing what I was just talking about, with several different species that are known to have resistance mechanisms in them, such as Staph aureus, Enterococcus faecalis, and faecium, Pseudomonas aeruginosa, Acinetobacter, and the last one there is Candida, which is a fungus, so we're not particularly interested in that. So the continuing rise in antibiotic resistance necessitates new or novel antimicrobial agents to combat them. So these new agents must be effective against resistant organisms and these resistance mechanisms that have developed, such as MRSA and VRE. So either you can create new semisynthetics using older backbone structures, such as, well, the relevant one in this particular case would be tetracycline, or penicillin is one that's used quite a bit, or you can find new agents with de novo activity, which is not what we're going to be covering in this presentation. So here's a graph I made of, on the top of the timeline, you see the introduction years of new antibiotics, and the lines are color-coded to the class of antibiotic they are. So all the penicillins have an orange line, or all the structures derived from penicillin have an orange line, and so forth. On the bottom, you see the years that resistance was observed in for these particular antibiotics. And obviously the bottom's not completely conclusive. There's a lot more lines on the top than on the bottom. But essentially what I wanted to show was that resistance pops up almost immediately after introduction, usually because the drugs are being used or tested before they're released on the market. And because we're dealing a lot of times with semisynthetic derivatives, the resistance mechanisms only have to be modified a little bit by the bacteria for them to now effectively work against the new antibiotic. So one of the things that makes the antibiotic field and infectious field a little difficult or a little undesirable is the idea that nature and mankind has already provided a huge list of potential targets. So unlike other drug markets where finding a drug target is one of the big hurdles to overcome, in the antibiotic market there's already a huge selection of targets. That's not to say you can't find new ones, but it's much easier just to use the ones that nature's already shown us. And that includes things like the bacterial ribosome, the cell membrane, folic acid synthesis, DNA replication, RNA transcription, and so forth. And here in this table, which is a little complicated, you see this. So you see like the targeted process, the antibiotic classes that affect them, and then any subclasses that would be relevant. So that's beta-lactams, or the famous one that has a bunch of subclasses. Different methods of resistance. So you see here that there's all types of methods of resistance, and some of them have developed multiple methods of resistance. Then the specific target, the phenotype of what happens to the bacterium when it tries to grow in the presence of these antibiotics, and then some common antibiotics that fall into these classes. So Tygacil is approved for a couple of things. Complicated skin and skin structure infections, CSSSI, and in this field it has competitors in daptomycin, linezolid, torzolid, vancomycin, Avalox, and Teflaro. And obviously you can see the a lot of those are the brand names, but you can see the structure names next to it. The second major grouping that it's indicated for is complicated intra-abdominal infections, or CIAI. And the competitors here are meropenem, imipenem and celastatin, menotinidazole, and I'm not very good at pronouncing this one, ceftriaxone. So, except for meropenem, these are all used in these are commonly used in combinations, and we're actually going to talk about the imipenem celastatin later on in one of the clinical trials. Another thing that Tygacil is used for is it's commonly used in the treatment of multi-drug resistant Acinetobacter species. And this is kind of a big deal because this particular species has been very tough to deal with in hospital settings. It has not been approved for this, and I'll mention this later, but it is commonly used for this. And one of the main reasons it's commonly used is because the competitors are colistin and polymyxin B, which are related to each other. And these two competitors were discovered quite a while ago, multiple decades, maybe probably up to 30 years ago. But they've only been deployed recently in medical use because they're highly toxic, or, you know, very toxic, not highly toxic. Obviously the human body can take it, but they can't take too much of it. And the reason they're used, the need for antibiotics to treat these resistant organisms has now trumped their toxicity. So tigecycline, or Tygacil, is now commonly used for that same area. So the burden of disease is that 70% of hospital-acquired infections demonstrate resistance to at least one antibiotic. And a lot of times what you're going to find in a hospital setting, if any of you are nurses or doctors, well, I'm not a medical doctor, but that you would know is that a lot of people that have these resistance organisms, these organisms will actually have multiple resistances. So a famous one is the Klebsiella penicillin resistance mechanisms actually give resistance. This is one enzyme that gives resistance to pretty much all the cephalosporin, penicillin, the vast majority of the beta-lactam class antibiotics. So it makes it very difficult. And then these organisms will be carrying plasmids, or can have them integrated into their genome. Multiple enzymes that are giving resistance, or efflux pumps that are giving resistance to different antibiotics, such as tetracycline, and so forth. So in the U.S., there's 2.5 million of these complicated skin infections annually, and it's estimated that the annual cost of treating these resistant bacterial infections ranges from $4 to $5 billion. So there's a large amount of money to be made trying to fix this, or saved.